Hello. In the previous lecture, we proved the following important result about finite field extensions. We showed that if E over F is a finite field extension and G is a finite subgroup of the group of automorphisms of this extension, when we consider the fixed points of this group action, meaning we look at all the elements inside the larger field that are fixed by all the elements of this group, then we get an intermediate field, and the extension of E over this intermediate field is a Galois extension. So again, let's make sure that we understand which field and over which field is Galois. So E is at top, F is our base field, and we are considering the fixed points, which is going to be an intermediate field, and the top portion is going to be Galois. As we will see later in this course as well, often the top portion satisfies the same rule, the same properties as the whole tower. So it's easier for the top portion to satisfy various properties of field extensions than the bottom one. This is a general kind of rule of thumb. Okay, now this is what we proved in the previous lecture. What we want to do in this lecture, at least at the beginning, is to understand the index of this field extension. In fact, we want to show that the index of this field extension is precisely the cardinality of the group G. And then we will use this to show that the group of automorphisms of this field extension, meaning fix of G linear isomorphisms from E to E, is precisely the group G that we started with. And that would be one of the important parts of the so-called fundamental theorem of Galois theory. Okay, so in order to show this result, we have to start with the following lemma. And what does it say? Suppose that G is as above, meaning G is a subgroup of the group of automorphisms of E. So here I don't need to start with a field extension. I can take any subgroup of the group of automorphisms of an arbitrary field E. And I don't need to assume that G is a finite group. It can be an infinite group. So G is a subgroup of the group of automorphisms of E. Then I can consider an action of this group on the vector space E to the n by letting it act component-wise. So meaning for every theta in this group, I let theta of a vector in E to the n be the theta of the first component, theta of the second component, and so on. Okay, now suppose I give you a subspace of E to the n with the following properties. First of all, this subspace is not the zero subspace. It definitely has a non-zero vector. And second, it is G invariant. What does that mean? This means if I give you a vector inside this space and I let the group G act on it, I'm going to be still inside this space. So whenever you have a G action, whenever a group acts on some set, we say a subset is G invariant if under the group action, I don't go outside of this set. So here I'm asking for this subspace to be G invariant. So these are the two assumptions that we are imposing on this subspace V. And then I want to deduce that it has a non-zero G fixed point, a point that is fixed under the group action G. Again, because the group action is component-wise, the set of fixed points is nothing but the set of fixed points inside the group, inside the field, raised to power n. So I'm considering the fix of G as a subfield of E, and then each component should be one of those elements. And then when we say G fixed points of V, I'm saying that I'm looking at the intersection of the subspace V with the fixed points of G raised to power n. And the claim is that I can find a non-zero vector inside this intersection. Okay, so let's see how the proof goes. The technique that we are using inside this proof is a very useful trick useful technique, and it appears one uses the same trick in different situations. So it's a good thing to get familiar with. So what is the technique? For every vector inside e to the n, I can talk about, let's say, the length of the support of C, some function of the vector. What is it? So for every C inside this vector space, I let L of C be the number of non-zero components of C. So of course, if C is the zero vector, L of C would be 0. Otherwise, C has some non-zero component, and therefore L of C would be a positive integer. In fact, some integer from 0 to n in general. So L of C is definitely some integer from 0 to n. It tells me how many non-zero components C has. Again, because I'm assuming V is a non-zero vector space, this set, the set of all the possible values of L of C, does contain a non-zero integer. Among all the non-zero integers, let's pick the minimum. So let M be the minimum among all the non-zero elements of the values that L of C can take as C ranges in the set of non-zero vectors of this vector space. And let choose one of those, and suppose that the vector C actually gives me that minimum. After rearranging the components, I can assume that the non-zero components are concentrated at the beginning and the rest of the components are 0. So without loss of generality, I can assume that my vector is of the form alpha 1, alpha 2, alpha 3, alpha m, and the rest of the components are 0. Now, what I am going to show is that this vector itself, after modifying it slightly, is going to be inside the set of fixed points of the group G. So let's see, what do I mean by that? Okay. But before I get to that part of the argument, let's point out what it means for the minimum of L of C's be m, and L of this particular vector C is m. What does that imply in general? So because the minimum of L of C is among all the non-zero vectors of V is m, that means if I happen to find a vector inside V that has L of C prime strictly less than m, then I can deduce that this is the 0 vector, because m was supposed to be the minimum among all the non-zero ones. And this is a kind of, this is the crucial observation that's going to help us to deduce the desired result. And what is going to be our mechanism? We are going to start with this minimum guy, with C, and then I'm going to do certain algebraic manipulations, but I make sure that each time I will be still inside the vector space V. I will not go outside of this. But then at the end, I make sure that the number of non-zero components will be less than m. And therefore, by this observation, I should end up getting the 0 vector. And that would give us the desired result. So again, the trick is to manipulate C to end up getting, turning one of the components to 0, getting less non-zero components. From there, we managed to deduce that the resulting vector is 0, and that would help us to finish the argument. So that's the route that we are taking. First things first, what I'm going to do, I'm going to make one of the components of C, I turn it into 1. How do I do it? I know that all the alpha i's are not 0, and I know that V is a subspace. Because V is a subspace, it is closed under a scalar multiplication. So it is closed under scalar multiplication. And alpha 1 is not 0, so I can talk about alpha 1 inverse. So because C belongs to V, V is closed under a scalar multiplication, I deduce that alpha 1 inverse times C is also inside V. So this way, I end up getting a vector inside V whose first component is 1, and still the L of this new vector is still minimum, is m. So in this process, I'm trying to make sure that L will be always at most m, and at the end strictly less than m, to get the desired result. So I end up getting this vector 1, beta 2, beta m inside V. Now, notice that because V is G invariant, for every element of this group G, when I apply theta to this vector, I will be still inside the vector. Now, when I apply theta to 1, I get 1. Then I get theta of beta 2, theta of beta 3, and so on. So this means that these vectors, all of them, belong to the subspace B. Now, V is a subspace. So this means when I subtract these two vectors, it will be still inside V. So this vector, which is 1, beta 2, beta m, and 0, 0, 0, 0, minus 1, theta of beta 2, theta of beta 3, and so on, 0, 0, 0, 0, is still inside V. But notice what are the components of this subtraction. The first component is going to be 0 now, because it's 1 minus 1. And the second component is beta 2 minus theta of beta 2, beta 3 minus theta of beta 3, beta m minus theta of beta m, and the rest of the components are 0. And this is still inside vector space B. And notice that L of this vector is strictly less than m, because except these components, the rest are 0. So I definitely have at most m minus 1 non-zero components. So L of this vector, which is still inside V, is strictly less than m. Therefore, by this type of argument that we've mentioned over here, we deduce that this vector is the 0 vector. So this means that this vector, this difference, which is inside V, is the 0 vector. That means theta of this vector, no matter what theta we pick, is inside, is the same vector. So this means what? This means that this vector is indeed, this means that this vector is indeed a non-zero, because the first component is 1, element of V, which is fixed under the group action by G. And we get the desired result. Okay, let's see how this helps us in order to understand the fixed points of a group action acting on a field E. So we are going to show the next proposition, which is about finite subgroups of automorphisms of a field. So suppose E is a field, G is a finite subgroup of the group of automorphisms of E. Then I look at the fixed points of G, and claim is that the index of this field extension that we have already proved is definitely a Galois extension. We show that it is going to be at most, the index of this extension would be at most cardinality of G. So to be more precise, we haven't proved that this index is, this extension is Galois yet, because so far we've worked with a finite extension and a subgroup inside the automorphisms of that extension, and there we showed that E over the fix of G is a Galois extension. A priori, at the moment, we don't know if this is a Galois extension. We will discuss it in the next theorem, that it is indeed a Galois extension. But for now, our emphasis is on this result, that the index of this extension is at most cardinality of G. Okay, so let's see how we can do. We are going to proceed by a contradiction. So suppose distinct elements of the group G are sigma 1, sigma 2, sigma n, and the first one is the identity. Okay, I have the identity map, and then sigma 2 and so on. It's a group, And suppose that these are the distinct elements of this group. So it has n elements. And suppose, to the contrary, that this extension, E over the fix of G, the index of this extension is more than n. And that's equivalent to saying that I can find n plus 1 linearly independent elements inside E. K linearly independent, where K is the fixed points of G. We already know that fixed points of a subgroup of group of automorphisms is always a subfield. So K is a subfield. I'm thinking about E as a K vector space, and I'm assuming that the dimension of E as a K vector space is strictly more than n, which is equivalent to saying that I'm assuming, to the contrary, that there are n plus 1 K linearly independent vectors. And let's call them E1, E2, E sub n plus 1. Now, I have n maps from E to E. I have n plus 1 elements from E. So we don't have that many choice. We apply our maps to E sub i's and put them in packages, look at them at the same time. So what do I mean by that? I apply sigma 1 to E1. I apply sigma 2 to E1. I apply sigma and so on. So I apply sigma 1 to EI, sigma 1 to E, sigma 2 to EI, and put them in the components of a vector inside E to the n. So V1, V2, Vn plus 1, these n plus 1 vectors, they are inside E to the n. I'm giving you n plus 1 vectors in E to the n. Remember, dimension of E to the n as an E vector space is n. Now I'm giving you n plus 1 vectors inside this vector space. So they should be linearly dependent. Okay, what does that mean? This means if I consider those vectors, this means when I say that they are linearly dependent, it means they satisfy linear equations of this type. I can multiply the first one by a scalar inside E, the second one by another scalar inside E, and so on. I can multiply them by scalars C1 Cn plus 1. They are coming from the field E, and then what I'm saying when we say that they are linearly dependent, it's the same as saying that the set V is indeed a non-zero set. It has a non-zero vector. So that's equivalent to saying that these vectors are E-linearly dependent. Okay, so now the first claim is that this is not any set. It is indeed a subspace of E to the n plus 1. So the non-zero part we have already discussed, that it is non-zero. It has a non-zero vector because they are E-linearly dependent. So this is equivalent to saying that this set has a non-zero vector. But now I claim that it is indeed a subspace. That means what? I need to show that it is closed under subtraction and it is closed under scalar multiplication. So I pick two vectors inside V and I need to argue why it is closed under subtraction. What does it mean that C is inside V? It means when I pick the components and use them to write down the linear combination of VI's, I end up getting 0. When I do the same with components of C prime, I end up getting 0. Now it's enough to subtract these two equations. After doing the subtraction and using distribution property in vector spaces, I end up getting that linear combination of V sub i's in terms of Ci minus Ci prime is also 0. And that's the same as saying that the difference between these vectors belong to V. So this shows that V is indeed closed under subtraction. Now if I pick a scalar E inside this field and multiply the vector C inside the vector space V, I want to argue that it is inside this vector space again. That means I need to say why, when I take the linear combination of V sub i's with coefficient C times E times C sub I will still get 0. But that's clear because I can factor it out, and then I know because C belongs to V, this linear combination is 0, and therefore this summation is also 0. Okay, so this shows that when I multiply the vector C by the scalar E, I am still inside the set V, which together with the previous step shows that V is indeed a subspace. So I get that V is a subspace, is a non-zero subspace of this vector space. Okay, now where am I getting to? I want to use the lemma that we have and argue that inside V I can find a G fixed point, a non-zero G fixed point. We will see why it is useful. By the lemma, let's take a look at it again. Where is the statement? So by this lemma, if I give you a subspace of e to the n, as soon as it satisfies two properties, first it's not zero, second it is G invariant, then immediately we can deduce it has a non-zero G fixed point. Okay, so now we have already argued that it is a non-zero subspace. Now I want to argue that it is indeed invariant under the group action by G. So I pick some elements inside the group. So let's call this guy a sigma. I pick a vector inside V, and my argument, my claim is that sigma of this vector is still inside V, and therefore V is G invariant. This is what we want to show. Okay, so what does it mean that C is inside V? It means that this linear combination is 0. What does this mean? This means that all the components are 0. Now, if you think about it, the jth component of V sub I is what? Or, okay, so the jth component of V sub I is what? So let's write this down. So V sub I is given by sigma 1 E1, sigma 1 EI, sigma n EI. So when we say that the sigma Ci Vi is 0, that's equivalent to saying that sigma Ci sigma j of EI is 0. And notice that these guys range over all the elements of the group. So it's equivalent to saying that for every element inside the group G, when I look at this linear combination, Ci's sigma prime of EI, I end up getting 0. That's exactly what we have over here. Okay, so this is what we have over here. For every sigma prime, when I look at sigma Ci, sigma prime of EI, I end up getting 0. Now, let's apply sigma to both sides. So this sigma that we have over here, I'm going to apply to both sides of this equation. What do I end up getting? I get, notice, remember, sigma is an element of automorphisms of the field E. And these elements, all of them, are inside E. So I can sigma preserves addition and multiplication inside E, so I can write it like this. I get that it's a linear combination of sigma of Ci's sigma of sigma prime of EI. And this is supposed to be 0. But again, notice that sigma prime is an arbitrary element of the group. Therefore, sigma composed with sigma prime is an arbitrary element of the group. So when sigma prime ranges inside the group, so does the composition of sigma and sigma prime. So you see, sigma is a fixed element. I'm composing it with the entire elements inside the group. I get back all the elements of the group. So this means that this element over here is an arbitrary element of the group. It can be anything we want. This means for every j that you give me, sigma EI, sigma of CI, and then instead of this blue guy, I'm going to plug in sigma sub j. So I get that sigma sub j of EI, the summation is going to be 0. So again, I'm replacing this composition. We notice that this composition can be any element inside the group. So I'm plugging in sigma sub j instead of that composite. But this means that this is true for every j, and so on. That means that all the components of this linear combination are 0. Because the jth component is exactly this summation that we have over here, and it's supposed to be 0. So this means that this linear combination is 0. That means sigma of this vector is still inside the vector space V. So we end up getting a vector space that is a vector subspace of e to the n plus 1 that is not 0, and it is invariant under the group action regime. And so by the lemma that we have proved, we deduce that V has a non-zero element inside the fixed points of the group raised to power n plus 1. So I can find some vector inside k to the n plus 1 that is inside V. Let's see what it means. So suppose that this is a non-zero a sub 1 dot a sub n plus 1 is a non-zero element inside k to the n plus 1, which is also inside V. This means that this linear combination is 0. In particular, the first component of this linear combination is 0. But what is the first component? The first component of V sub I, what is it? The first component of V sub I, remember, it is sigma 1 of E sub I, and then we go like this. But the first sigma 1 is the identity map, remember? We arranged it in a way that sigma 1 is the identity map. So the first component of V sub I is indeed E sub I. I don't know about the other components. The other ones depends on the choice of these sigmas and so on. But I don't care. What I care is the first component. I'm looking at this linear equation, and then I'm focusing on the first component. Knowing that this linear combination is 0, I deduce that the first component of this linear combination is 0, which means I get that sigma a sub I, E sub I is 0. Remember, a sub i's are inside K. Here we have them, that a sub i's are inside K. So this means I am getting a non-trivial K-linear combination, a K-linear relation between E sub i's. I'm getting that E sub 1, E sub 2, E sub n plus 1 are K-linearly dependent. That's a contradiction, because we assume they are not. Remember, we started by the contrary assumption. We assume that the dimension of this vector space, the dimension of E as a K vector space, is more than n, and then from there we found, we chose this n+1 k-linearly independent vectors and then continued. Now at the end, we deduced that they are k-linearly dependent. And that's a contradiction that shows the claim, that shows that dimension of E over the fixed points of G cannot be more than the cardinality of the group G. Okay, now let's see what is the consequence of this. Suppose E is a field and G is a finite subgroup of the group of automorphisms of E. Then, first of all, E over the fixed points of G is Galois. The index of E over the fixed points of G is precisely the cardinality of the group. And the group of automorphisms of E over fixed of G, the fixed of G isomorphisms or automorphisms of E is precisely the group G that we started with. Okay, this is one of the important results in Galois theory that we are going to prove. So again, E is a field, G is some finite subgroup of the group of automorphisms. I look at the extension of E over the fixed points of G, then I look at the automorphisms of this field extension, and the claim is that this is precisely the group G that we started with. And the extension E over the fixed points of G is a Galois extension, and the degree of this extension has the same cardinality, is the same as the cardinality of the group G that we started with. Okay, so let's see how the proof goes. So let's denote the fixed points of G by F. By the previous proposition, we know that the index of this field extension is at most the cardinality of the group, and therefore it's a finite extension. Now that it's a finite extension, and also let's point out that the group G, every element, when I restrict it to the fixed points of G, is like identity, and therefore G is a subgroup of fixed of G automorphisms of G, E. Again, the point that I'm raising here is that for every theta inside the group, when I restrict it to the fixed points of this group, clearly I get just identity function. So therefore, it is indeed a subgroup of the fixed G linear maps, linear automorphisms from E to E. So I'm giving you a subgroup of a group of automorphisms of a finite extension E over F. Now we have proved, as we mentioned here, we have proved that when I start with a finite field extension and I give you a finite subgroup of the group of automorphisms of this field extensions, then E over the fixed points is a Galois extension. And therefore, here we are getting that E over the fixed points of G is a Galois extension. Okay, so it's a Galois extension. It is one of the important results that we have. But what does that mean that it's a Galois extension? One of the things that we showed for finite extensions is equivalent to saying that it's a Galois extension was about the cardinality of the group of symmetries of this extension, meaning when we say this extension is Galois, that implies that the index of this extension is precisely the cardinality of the group of automorphisms of this field extension. But again, as we have pointed out, this group of automorphisms contains the group G. So that means this index is at least cardinality of the group G. Now, by the previous proposition, and as we have pointed out over here, cardinality of the group G is at least the index of this field extension. So everything is sandwiched between the same two numbers. So all of these numbers should be the same. So altogether, we deduce, first of all, the cardinality of these group of automorphisms of the field of this field extension and the group G are the same. And so, because G is a subset of this group of the group of automorphisms of this field extension, they should be the same groups because they are finite groups, they have the same cardinality, and one is a subset of the other one. We deduce that they are the same. Second, the index of this field extension is precisely cardinality of this group because it's Galois, and the same this is the case, and so on. So we proved all the things that we claimed. We showed that the automorphisms of E, the extension of E over fix of G is precisely G. The index of this extension is precisely cardinality of the group G, and this extension is a Galois extension. So this shows this theorem. Now, as an immediate corollary, we end up getting a new criterion for a finite extension to be Galois. So what is it? So suppose I start with a finite extension. This finite extension is Galois if and only if the group of automorphisms of this extension is rich enough so that it moves everything inside E except those points that are inside F. So alternatively, how should I say it? The set of fixed points of the automorphisms of F automorphisms of E is just F. Everything outside of F is moved by some element inside the group of automorphisms. So that's equivalent to saying that this field extension is Galois. Okay, let's see how the proof goes. So let's go from left to right. So assume that E over F is Galois. What does that mean? Again, it means that it's normal and separable, but we show that for a finite extension is Galois if and only if the cardinality of the symmetries of this extension is the same as the index of the extension. But at the same time, we know that when I take the fixed points of this extension, so the full group of automorphisms, if I call this guy G, if I call this group G, then we showed that the cardinality of G is the same as the index of the fixed points of G inside E. This is what we have over here in the previous theorem. Now I'm applying this result for the group G, where G is the entire group of automorphisms of this extension E over F. Now, by the previous result, we know that this cardinality of this group is the same as the index of this field extension. But notice, F is a subset of this field extension. Now we can apply the Tower theorem. Now, again, let's write down what I'm saying. So I have E, or maybe I use blue. I have E at top. Then I have the fixed points, these fixed points. And then I have F. And it turns out that these two have the same. So it turns out that this index and this one over this one over this one are the same. So both of them are the same as the cardinality of this group. So they are the same. Therefore, I can use the Tower rule and deduce that the index of the lower part is 1, which means that these two are the same fields. So F is precisely the fixed points of this group. Okay, so this shows that left implies right. Now let's go from right to left. But that's rather easy because when I have the right part, I'm getting that F is indeed fixed points of this group. And whenever I give you a group and I look at the fixed points of that, we show that E over the fixed points is a Galois extension. And that gives me the left-hand side. Okay, so now this is a new criterion for an extension to be Galois. So E over F is Galois if and only if the fixed points of this extension is precisely F. Okay, now we have all the needed tools in order to prove the fundamental theorem of Galois theory. The fundamental theorem of Galois theory has many parts. I'm going to split it into two theorems in order to give them enough emphasis. So the first part, or the first theorem of fundamental theorem of Galois theory. So what is it? It gives us a concrete bijection between subgroups of the group of automorphisms of a finite Galois extension and intermediate subfields. Okay, so let's see what it is again. The fundamental theorem of Galois theory. It tells us that suppose E over F is a finite Galois extension. Then I look at the set of all the intermediate subfields. So this is the set of all the intermediate subfields of this field extension. On the other hand, I look at all the subgroups of the group of symmetries of this field extension. Now, if I start with a subfield, I can look at all the k-linear maps, k-linear automorphisms from E to E. So that would be my psi. So psi of a subfield is nothing but k-linear automorphisms from E to E. Now, when I start with a subgroup H, I can look at the fixed points of the subgroup, and I'm going to get an intermediate subfield. So indeed, I'm getting maps from the set of intermediate subfields to subgroups of automorphisms of this field extension, and vice versa. And claim is that these two maps that I'm giving you, they are inverse of each other. So that's the claim. So I'm giving you a very concrete bijection between these two sets. Okay, let's see what it means. What am I claiming? I need to show that composite of these two maps is identity. So psi composed with phi is identity, and similarly phi composed with psi is identity. This is what I need to show. Again, what does that mean? This means that I need to show that if I start with a subgroup H, then when I apply phi to H and then psi to phi of H, I need to show that I'm getting back H. This is what I need to show. But let's see what it means. Phi of H is the set of fixed points. So this is phi of H. And what we showed is that H over phi of H is Galois, and the group of automorphisms of E as fix of H linear automorphisms of E is just H. And that's exactly what we wanted to show. This is this result that we showed over here, that this result that we showed over here, where is it? No, not here, here. Over here. The group of automorphisms of the extension E over fix of G is just G. When I change the name of G to H, is exactly what we have over here. And that's equivalent to saying that psi of phi of H is H. Okay, so far so good. We showed that one of these composites is identity. Now let's go the other way around. So I'm going to start with with an intermediate subfield K, and I want to show that when I apply psi to K and then look at phi of that, I get back to K. So again, let's try to understand what it means. I need to show, again, we need to show, let's write it over here before we continue with the proof. We need to show that phi of psi of K is K. So let me put this, give myself a bit more space. This is the same as saying that I need to show the set of fixed points of automorphisms, of K automorphisms of E is just K. Now this is what I need to show. Now look at what we have. Look at this corollary. The set of fixed points of automorphisms of a field extension is the base field if and only if the field extension is a Galois extension. Of course, when it is finite. We already know that it's a finite extension because everything is finite over every extension is a finite extension. We are working with intermediate subfields anyway. So this means in order to show the claim, in fact, the claim is equivalent to saying that E over K is a Galois extension. So again, we have proved that this claim is equivalent to saying that E over K is a Galois extension. So this is what I need to show. As soon as I show E over K is Galois, so here I'm claiming that every intermediate subfield that I pick, E over K will be immediately Galois. And if I show this, we are done. Because that implies that the fixed points of the group of automorphisms of this extension is just the base, which is K, and that shows that the composite of phi and psi is identity. So in order to show that this extension is Galois, I need to show that it is normal and separable, which means I'm going to pick an arbitrary element of E, and I'm going to study the minimal polynomial of alpha over K. Okay, so let's pick an element alpha inside this extension E. I want to understand minimal polynomial of alpha over K, but for a second I think about what I know about my alpha, what do I know about E, F, and so on, before going and focusing on K. By our assumption, E over F is a Galois extension, and that's a crucial assumption that we are imposing here. That means that it's both normal and separable, and both of them have interpretations in terms of the minimal polynomial of alpha over F. Saying that it is a normal extension is equivalent to saying that all the zeros of the minimal polynomial are already inside E, which means I can find alpha 1, alpha 2, and so on inside E, and write down the minimal polynomial as product of these linear factors. Saying that it is separable is equivalent to saying that alpha i's are distinct. Okay, so that means I can find distinct elements of E and write down the minimal polynomial as product of these distinct linear factors. Now, notice that all the coefficients of the minimal polynomial of alpha over F are clearly inside K as well, because F is a subfield of K. So this minimal polynomial is a polynomial in K bracket X, and it has alpha as a 0. Therefore, the minimal polynomial of alpha over K divides this polynomial. Remember, I want to understand if E over K is Galois or not. That means I need to study minimal polynomial of alpha over K, and that's what I'm doing now. I notice that minimal polynomial of alpha over K divides minimal polynomial of alpha over F inside the ring K bracket X, and therefore when I enlarge the ring, it still divides. So this means this minimal polynomial divides minimal polynomial of alpha over F in E bracket X. Why do I enlarge and go to E bracket X? Because I already know irreducible factors of this guy in E bracket X, and they are all linear, and they are all distinct, and they are X minus alpha i's. Knowing that a polynomial divides it we deduce that all the irreducible factors are subsets of the irreducible factors of the guys that we have already written here, which means the minimal polynomial of alpha over k can be written as a subproduct of these irreducible factors. I can choose some of them, multiply them, and end up getting the minimal polynomial of alpha over k. From here, what do I deduce? First of all the zeros of this minimal polynomial are already inside E. I can write it as product of linear factors over E. Second, all of these linear factors are distinct. So that shows that E over K is both normal and separable. So again, because I wrote this minimal polynomial as product of distinct linear factors, monic linear factors. From here, we deduce that E over K is a Galois extension, because this is true for every element inside this. We deduce that it's a Galois extension. Now that it's a Galois extension, we deduce that the set of fixed points of the group of automorphisms of this extension is just K, and that's exactly saying phi of psi of K is K. Okay, now, again, let's make a few remarks about what we have proved and what we can get a bit more. So one remark, as I've mentioned, is that if I tell you E over F is a Galois, here we use the fact that it is finite as well, but not really. So if you go and look at the proof over here, we see that if I tell you E over F is Galois, then I can write down the minimal polynomial of alpha over K as these products. Then I can run the same argument and deduce that in that case, E over every intermediate subfield will be also Galois. So again, it is compatible with the rule of thumb that I've mentioned earlier, that whatever property I give you about E over F, often, not whatever, but often these properties are inherited at the top portion of the tower. So if E over F is Galois, then E over every intermediate subfield is also Galois. Okay, so this is one of the things that we proved. Later we will see that often K over F is not Galois, but I mean, we will in fact give a necessary and sufficient condition for K to be a Galois extension of F in terms of group theory, but we'll go back to that later. The other thing that we notice is that these psi and phis, they are inverse of each other, and they are order reversing. So what do I mean by that? So suppose that I give you intermediate subfields and one is contained inside the other one. So these are intermediate subfields. I apply psi and I get groups. What are the groups that I get? I get group of K1 linear automorphisms and K2 linear automorphisms. Because K2 is contains K1, when I tell you some automorphism is K2 linear automorphism, if it is linear under the larger field, of course it's linear under the smaller field. So every K2 linear automorphism is definitely a K1 linear automorphism. So psi of K2 is contained inside psi of K1. So it is reversing the order. Let's also point out that the full, psi of F, the smallest field inside this, among the intermediate subfields, is the full group of automorphisms of this extension. And psi of the entire field, which means what are the E linear maps from E to E? That's just identity, because it's supposed to be restriction to E is supposed to be identity. So here I only get identity. So as you can see, it's a reverse, order reversing map. Similarly, we have the same phenomena for the inverse map for phi. Let's try to digest it a bit better. So if I give you two subgroups, one is contained in the other one. When I look at the fixed points of H1, okay, when I look at the fixed points of H2, the larger one, If it is fixed under the larger one, of course it's fixed under all the elements inside this larger one, and therefore it's fixed under the smaller subgroup H1. So the fixed point of H2 is contained inside the fixed points of H1. So I get, again, the order reversing property for the function phi. Let's also point out that the fixed points of the trivial group is, every point is fixed under the trivial group, so I get the entire field. And the fixed points of the entire group of automorphisms of this field extension, because the extension is Galois, is just the base field. So we get this order reversing property for both phi and psi, and they are bijections. Now let's write down the second part of the fundamental theorem of Galois theory. So in this second part, we get, so far we have this bijection between intermediate subfields and subgroups. Next, we explore between the connections between the index of the subgroups, index of the subfield extensions. We explore about certain properties of the extensions. So do we get a normal extension over the base field or not? So we have already discussed that the top one over this guy is always Galois. But then we discussed that the intermediate field over the base field is a normal extension, precisely when phi of that, psi of that intermediate field is a normal subgroup of the group of automorphisms of this extension. And finally, we point out that if I tell you an intermediate field is a normal extension of the base field, then it is a Galois extension. The separability is something that can be inherited for the bottom part as well. We don't show this full generality. We only discuss it for Galois extensions for now. We'll come back to this separable extensions later. Okay, but let's see again what are the statements. So the setting is that E over F is a finite Galois extension. I'm looking at the set of all the intermediate subfields and the set of all the subgroups of the symmetries of this intermediate, of this field extension. I'm looking at psi and phi as before, meaning when I give you a subgroup, I look at the fixed points. And when I give you then an intermediate subfield, I look at the k-linear automorphisms from E to E. So remember, I'm here always working with automorphisms of the top field. But whenever I give you intermediate fields, I'm asking for my automorphism to be identity when I restrict it to this subfield. Or I'm just looking at the k-linear maps. Okay. So these are phi and psi. We have already discussed that these are inverse of each other. Now we will see that they in fact satisfy many interesting properties. So for instance, if K1 and K2 are two intermediate subfields and one is contained in the other one, we have already discussed that then psi of K1 contains psi of K2. So I can talk about the index of the subgroup inside the other one. And the claim is that the index of this subgroup is equal to the index of the field extension K2 over K1. Okay, so now similarly, we have the other way around. So if I give you H1, a subgroup of H2, both of them subgroups of the automorphisms of this field extension E over F, and then I apply my phi and look at the fixed points of H1, fixed points of H2. Fixed points of H2 is contained inside the fixed points of H1. If something is fixed under the larger group, it's definitely fixed under the smaller group. Now, these are intermediate subfields. One is contained the other in the other one. I can talk about the index of this field extension, and claim is that index of this field extension is equal to the index of the subgroup H1 inside the subgroup H2. Okay, so the first part is about relation of the indexes one as subfield, one as field extensions, the other one as subgroups. The second part of the claim is about connection between being normal as a group and getting a normal extension over the base field. Again, let me emphasize that when I tell you E over F is Galois, then immediately I know, no matter what I pick as an intermediate field, so the top portion is always Galois. This portion is always Galois. But this portion is not necessarily normal, is not necessarily Galois. And what we are emphasizing over here, what we are getting over here, is in fact a necessary and sufficient condition for this part to be Galois. In part 2, I'm working with normal, but in part 3, I point out that if something is normal, then it is Galois, and the other way around is by definition. So in the third part, I'm saying getting a normal extension is equivalent to saying that we are getting a Galois extension. And the second part tells me that I get a Galois extension or a normal extension precisely when, after applying psi, I end up getting a normal subgroup of the group of symmetries of this field extension. So psi of k is a normal subgroup precisely when the extension of k over the base field is a normal extension. And the other way around. So if I tell you that N is a normal subgroup of the group of symmetries, that happens if and only if phi, or the fixed points of N over the base field, is a normal extension. So we see that these maps phi and psi respect being normal in these two different meanings. One, normal over the base extension, over the base field. The other one, a normal subgroup of the symmetries of this field extension. And as I have pointed out, the third part is about equivalence of getting a normal extension over the base field and getting a Galois extension over the base field. So if I tell you something over the base field is normal, then I deduce that it is Galois over the base field. And we will discuss it later. I mean, you see, Galois means normal and separable. We will discuss it later that if I tell you E over F is separable, then not only E over K is separable, but also K over F is separable. So from there, we can also deduce this result. But here we are going to focus on Galois extensions and get this claim. So this theorem 2 can be considered as another part of fundamental theorem of Galois theory. So again, a fundamental theorem of Galois theory gives us a extremely good understanding of intermediate subfields in terms of subgroups of the group of symmetries of this field extension, assuming that E over F is a finite Galois extension. Let's prove parts 1 and 2 and so on. Let's start with part 1. We already know that the cardinality of the group psi of k, again, psi of k is the group of k automorphisms of E, and we know that the k group, because we have proved that E over k is Galois, and therefore the group of k automorphisms of E is equal to the index of E over k. So cardinality of psi of k is the same as the index of k inside E. Now, when I look at the index of psi of k2 inside psi of k1, using Lagrange, we know it's the same as cardinality of the larger group divided by the cardinality of the smaller group. Now, when I use this equality over here for k1 and k2, we get that the numerator is nothing but index of the extension E over k1. And the denominator is nothing but the index of the extension E over k2. Now, if I use the Tower result, the Tower rule, I deduce that the index of E over K1 is product of these intermediate, the indexes of these two extensions, E over K2 and K2 over K1. So after simplifying, I get that it's precisely the index of the extension K2 over K1. And that's exactly the claim that we were looking for. This is exactly what we wanted to get. That index of this psi of K2 as a subgroup of psi of K2, K1 is the same as the extension, the index of the extension K2 over K1. Now, let's see the group theoretic side. Phi of K1 is an intermediate subfield. Phi of K2 is an intermediate subfield. By the previous result, we know index of these intermediate subfields is equal to psi, the index of the group, psi of phi of K2. So this one, I apply psi, it goes here. And this one, I apply psi, it goes over here because psi is order reversing. And then we know that the index of the subgroup inside the larger one is the same as the index of the field extension. But psi and phi are inverse of each other, so I'm getting back H1 and H2, and that's exactly the equality that we were looking for. Okay, so this gives us part one. Part two is a bit more subtle. So let's try to understand what it is. I start with a normal subgroup. So I'm going to show you this part, that if I start this part, this is what I want to show you. And then I'm going to use that phi and psi are in, okay, so then so this is the direction that I'm going. I'm going to show you that if n is normal, then phi of n over k is a normal extension. And then I focus on this. I tell you if k over f is a normal extension, then psi of k is a normal subgroup of the group of automorphisms. And then using the fact that psi and phi are inverse of each other, we can complete the picture. And I leave that to you. It's rather easy. So the key thing is to show that if n is a normal subgroup, then the set of fixed points is a normal extension over the base. Now, and if k over f is a normal extension, then the group of k automorphisms of E is a normal subgroup of f automorphisms. Okay, so let's see why this is the case. In fact, the second one we have already discussed, but I'm going to mention it later anyway. Let's start with the first one. So let's assume that n is a normal subgroup of the group of automorphisms of this field extension. We want to show that the fixed points of n over the base field is a normal extension. In fact, we will show that it is a Galois extension. What does that mean that it's a normal extension? This means that I have to look at the minimal polynomial of alpha over f and split it completely in fixed n. So let's start with minimal polynomial of alpha over f. What do I know about it? I know that E over f is Galois, is finite Galois. Therefore, we have proved in the previous lecture indeed that when I give you a Galois extension, then the minimal polynomial can be decomposed into linear factors, and all the roots are in fact in the orbit of automorphisms of E over f acting on alpha. So again, let me go back to the first lecture and show you this result if I can find it quickly. So it is over here that, yeah, it's over here actually. So it's over here, but this is over the group. Maybe I can do better than that. Yes, it's over here, that the minimal polynomial of alpha over f is product of x minus alpha primes, where alpha primer is ranging in the automorphism, in the orbit of automorphisms of E over f orbit of alpha under the action of the automorphisms of E over F. So this is what we had in the previous lecture. Now, so by that result, I can write down the minimal polynomial of alpha over F as product of, here I should have said this one. This is what I wrote is not quite correct. I should write it like this, that it is alpha prime belonging to this one, the orbit of this guy. Now, my claim is that all the elements inside the orbit are already in the fixed points of N. So I pick, and so what I'm saying is that every element inside the orbit of alpha, if alpha is fixed by the normal subgroup N, then every element inside the orbit of alpha is also fixed by this normal subgroup. And therefore, all of these alpha primes are already inside the field fix N. Okay, this is what I want to show. As soon as I show this claim, we get that fix N over F is a normal extension, because that implies that this this splitting is already happening in fix N. Okay, so let's see. So what does it mean that theta of alpha is in fix N? This means I need to show that for every element of this subgroup N, of this normal subgroup N, for every sigma inside N, sigma of theta of alpha, I need to show that it is theta of alpha. Okay, I need to show that equality. Let's multiply both sides by a theta inverse. So that's equivalent to saying that theta inverse of sigma of theta applied to alpha is alpha. This is what I need to show for every sigma inside the normal subgroup. It's a normal subgroup, and I'm conjugating sigma. This is a normal subgroup. That implies that when I conjugate it, I will be still inside N. Alpha is supposed to be fixed by every element inside N. So alpha is fixed by every element inside N. This guy belongs to N. So it should fix alpha, and we get exactly the claim that we wanted. So we end up getting that this holds. Again, because alpha is in fixed N, and that guy is inside the fixed points of N. Okay, now the claim follows. What does that mean? This means all the zeros of M sub alpha comma F, all of them are already inside fixed N, and they are distinct because they are in the orbit. So they are distinct, and they are in fixed N. That implies that fixed N over F is a Galois extension. It's both separable and normal, therefore it's a Galois extension. Okay, so we showed that part of the claim, that every intermediate, so fixed points of a normal subgroup over the base field is a Galois extension. Now let's go the other way around. Suppose I give you a normal extension over the base field. And then we have proved this part, in fact, earlier, that because it's a normal extension, if I start with an automorphism of E, when I restrict it to K, I will be getting a well-defined group homomorphism. And it is indeed surjective as well. The kernel of this group homomorphism consists of K linear automorphisms from E to E, those automorphisms whose restriction to K is identity, that's the kernel, and that means that it's K linear, and that's exactly psi of K. So psi of K is the kernel of this map, and therefore it's a normal subgroup. So we showed both that if I start with a normal subgroup, the fixed points is a normal extension over the base field. If I start with a normal extension over the base field, then the group of K-linear automorphisms is a normal subgroup. Now, using the fact that psi and phi are inverse of each other, we get both sides if and only if, and that gives us the second point. And finally, Let's argue why when I give you a normal extension over the base field, it is also a Galois extension. So when I give you a normal extension over the base field, we have already proved that that implies that psi of k is a normal subgroup. But then we showed that when I start with a normal subgroup, the set of fixed points over the base field is going to be Galois. This is what we proved. And therefore, because that's phi of psi, I'm getting back k. Therefore, k over f is a Galois extension. This is again phi of psi of k equals to k is what we are using over here. So I'm using that, and therefore k over f is Galois. That's exactly what we wanted to show. Let's summarize what we have over here. We show that if E over f is Galois, then the top portion is always Galois. And we also argued that if we also argued that the bottom part is Galois exactly when the automorphisms, the k automorphisms of E over k, the k automorphisms of E is a normal subgroup of f automorphisms of E. So this is what we showed. An immediate corollary of this result is that if I tell you E over f is a finite Galois extension, then there are only finitely many intermediate subfields, because these intermediate subfields are in one-to-one bijection to subgroups of the extension, but the subgroup is a finite group. The group of symmetries is a finite group. So there are only finitely many subgroups. So there are only finitely many intermediate subfields. Now we can combine this result with the construction of normal closure and relax this condition of Galois a bit and get the following result. So if I start with a finite separable extension, then it has finitely many intermediate subfields. So the number of intermediate subfields of this extension is finite. So you see, from Galois now, all of a sudden I went to separable. But the key point is that when I start with a separable extension, then the normal closure is going to be a Galois extension. That's the key thing, as we will see over here. So again, what we are proving is that, so if L is a normal closure of this extension, then L over f is Galois. This is what we prove, and then we use the previous corollary in order to deduce that the number of intermediate subfields of E over f is finite. Okay, let's see how the proof goes. How did we construct the normal closure? We start with a base f basis of E. Then we look at the product of the minimal polynomials of alpha i's over the base field f. But because I want to make sure that my extension contains E, I consider splitting field of this polynomial not over f, but rather over E. So that way I guarantee that my splitting field contains E. So this way I'm guaranteeing that this L that I'm constructing, this L is an extension of E. Now my claim is that L is indeed a splitting field of the same polynomial over f. I don't need to the entire E in order to get it as a splitting field. But first I start viewing it as a splitting field of the polynomial f over E, the larger one. Then I argue that it is indeed a splitting field of the same polynomial over the smaller field. Notice that the polynomial is already inside f bracket x. This polynomial is already inside f bracket x. So there is no problem from the polynomial point of view. Okay, so let's try to understand what it means that it's a splitting field. This part we have already done we have already seen in the previous course, but let's go over it, make sure that we understand the proof. It's been a while. So L is a splitting field of this binomial over E. What does that mean? So this means, let me quickly go over this and then we stop. So L is a splitting field of this binomial over E. This means that I can split it completely over E. This means I can find over L. This means I can find these elements inside this larger field that are zeros of all the factors of F, which means all the factors, these are the minimal polynomials of the factors, I can factor them into linear factors. And moreover, when I add these zeros to the base field E, this time our base field is supposed to be E because I'm considering splitting field over E. When I add these zeros to E, I end up getting the entire L. Now, because E is a subfield of L anyway, I already have at least one zero of these minimal polynomials inside L, and those are alpha i's. So after rearranging these zeros, I can make sure that alpha I appears as the first one. So I'm assuming that alpha sub I1 is alpha I. That means when I change this E to F, the smaller field, and add these zeros to F, the ring that I am getting definitely contains the F span of alpha 1 dot alpha n, because these are among these zeros. The F span of these guys is the entire E, because that alpha 1 dot alpha n is an F basis of E, which means E is already inside this ring. And when I add all the zeros to F, it already contains E. Now I'm adding all the zeros, and the ring generated by E and these zeros gives us the entire L. So L is already generated by alpha i's and F. So again, what does that mean? This means the polynomial F can be split into linear factors, and when I add zeros of F to the base field F, capital F, I get the entire field L. That's the definition of being a splitting field. So L is a splitting field of the polynomial small f over capital F. Now notice that because E over F is a separable extension, that was my assumption, that was our assumption over here, because it's a separable extension, this is a separable polynomial. All the irreducible factors will be separable. So it's a separable polynomial. Therefore, L is a splitting field of a separable polynomial over the base field capital F. A separable polynomial. That is equivalent to saying that this extension is a Galois extension. So we just showed that the normal closure of this extension E over F is indeed a Galois extension. For a finite Galois extension, it's definitely finite because it's a splitting field of a polynomial. Now, for a finite Galois extension, we showed that there are finitely many intermediate subfields. Therefore, there are only finitely many intermediate subfields for the field extension L over F, and so there are only finitely many intermediate subfields of the extension E over F, because every such intermediate subfield is also an intermediate subfield of L over F. Okay, so we'll continue in the next lecture.